Why is it said that structural understanding is difficult? Without understanding, vibration engines cannot be built, and buildings cannot be constructed. The answer is simple: because almost all real-world, mechanical and architectural structures vibrate. If this vibration is not handled properly, the resulting structures will at best produce abnormal sounds, and at worst completely fall apart. Let's first look at this simple model: a heavy mass attached to a spring. Don't be fooled by its simplicity. It precisely captures the critical point of all complex structures, namely mass and stiffness. Specifically, the greater the mass, the slower the vibration, the stiffer the spring, the faster the vibration. To clearly observe this relationship, let's first make this block move only up and down, ignoring gravity and friction. This phenomenon of self-oscillation is called free vibration. The speed of oscillation is actually a battle between the spring's pulling force and the mass inertia. The spring desperately pulls back, while the mass due to inertia rushes in the opposite direction. This back-and-forth tug-of-war will eventually reach a stable rhythm. This rhythm is the natural frequency. Look at these two systems. The spring stiffness is identical, but one is heavy and the other is light. Therefore their vibration rhythms are completely different. The heavier one vibrates much more slowly. Take tuning forks for example. When you strike one, it always emits a single fixed pitch. This is its natural frequency. However, complex structures like buildings or engines have multiple natural frequencies. Observe this three-story model. At 0.9 Hz it exhibits uniform displacement in the same direction. At 1.9 Hz it shows S-shaped distortion. At 2.9 Hz it undergoes high-frequency violent oscillations. However, in reality, vibrations do not persist indefinitely. Energy is dissipated as heat due to frictional losses. The force that causes vibrations to disappear is called damping. For instance, the giant damper in Taipei 101 Skyscraper is specifically designed to counteract the building's sway. Even in strong winds or earthquakes, damping can stably suppress the amplitude, ensuring the building's safety. Let's demonstrate with this small motor, equipped with an eccentric mass. When its rotational frequency perfectly matches the system's natural frequency, the two values are identical. The rhythm precisely aligns. The vibration will instantly escalate. Therefore, even a small eccentric mass can infinitely amplify vibrations. In real-world engineering, the most famous resonance failure occurred with the Millennium Bridge in London. The bridge was urgently closed just 2 days after its opening, due to massive swaying. Whenever many people were on it, the bridge deck began to sway violently from side to side, forcing pedestrians to walk sideways to maintain balance. So why did it sway? Engineers measured and discovered that the bridge's lateral natural frequencies were very densely packed, distributed between 0.5 and 1 Hz. This is where the problem lay. When people walk, they exert not only vertical pressure, but their bodies also swing from side to side. The frequency of this lateral swing, around 1 Hz. This is typical resonance. Pedestrians' pace is precisely timed. They hit the bridge's natural frequency. More critically, there's also a hidden, synchronous lateral excitation physical trap. When the bridge sways, pedestrians, to avoid falling, instinctively spread their feet to maintain balance. As a result, thousands of people on the bridge automatically synchronize their steps. This is equivalent to thousands of people pushing a swing simultaneously. Energy accumulates wildly. The bridge naturally sways more violently. So what could be done? Demolishing and rebuilding would be too expensive. Reinforcing the structure would be too unsightly. Engineers finally thought of the dampers we mentioned earlier. They secretly installed two types of black technology beneath the deck. One is a viscous